Okay, yeah, now it's starting. Thank you again. I think that will continue. Yeah, so what I want to do is an example of histogram equalization. So suppose this is a hypothetical image, 8-bit, just a 4x4, so that we can do calculation by hand. So histogram equalization, as I described in the posted lecture, consists of, first you compute the histogram of the given image and then try to map it to the equalized histogram. Okay, so the description was there in the earlier lecture, and now we'll just see how the process goes. So first, the thing is to calculate the histogram of this image, right? So the histogram of this image. For this, we'll list down all the intensity values and the number of pixels with those intensity values, right? So the intensity values are K. Since this is an 8-bit image, the intensity values are from 0 to 7. So 0, 1, 2, 3, 4. And then we want to see how many pixels with those intensity values, right? So there are no pixels with the intensity value 0. 1 pixel with the intensity value 1, 2 pixels with intensity value 2, 2 pixels with intensity value 3, 1 pixel with intensity value 4, 2 pixels with intensity value 5, 2, 3, 4, 5, 6 pixels with intensity value 6, and 2 pixels with intensity value 7. Right? So, so these are the intensity, the number of pixels in with those intensity values, and you can, of course, calculate P of RK if you want. Okay, P of RK will be just dividing NK by the total number of pixels. The total number of pixels here is 16. So 0 by 16, 1 by 16, 2 by 16, and so on. Okay, but what we really require for equalization are these cumulative sums, right? So we require cumulative sums of NKs. So, well, here we have 0, then 1 plus 0, 1, 2 plus 1, 3. Okay. So cumulative sums from this column. So 0, 1, 3, 5, 6, 8, then plus 6, 14. And finally, of course, it should come out to 16. That is the total number of pixels here. Okay. So once we have got these cumulative sums, remember what SK was. Okay. If you want to do histogram equalization, remember the idea was that you have some number of given the intensity function or the intensity variable R. Okay, and then you apply some function T to it to generate an output image S. Okay, so you want to calculate or you want to have this S. Sorry, you want to have an S, the output image, whose histogram is sort of like the uniform distribution function, right? So to compute this S, we derived last time that in the discrete form, this will look like Sk equals Trk, okay? Where Trk, we found a formula for Trk. This is L minus 1 times summation P R J, J equals, J goes from 0 to K. Correct? So this was a formula that we found for Sk. So, and in each case, this PRK is NK divided by Mn. Okay. And so that is why, since we are going to sum these probabilities from 0 to K, we will require these sums of NK. So that is why we calculated this column of cumulative sums. Okay. Okay. So So now from this, let's try to calculate these SKs. Okay, so just apply this formula. For 0, this is going to be, so L minus 1, L is 8 here. Correct? Here L is 8. So L minus 1 is 7. So the first, for k equal to 0, S0 is going to be 7 times 0, which is 0. Okay. Then S1 is going to be 7 times, well, you just want to look at PR1. So this is 1 by 16. So this is 7 by 16. Okay. Then 7 times PR1 plus PR2. Okay. So that's going to give me 2 by 16 plus 1 by 16. That's 3 by 16. Okay. So this comes out to, so I've calculated these values. So this is approximately 0.4. This comes out to 1.31. Okay, and so on. Okay, so 7 times. So whatever the next value here. Okay, so the next value here would have been 2 by 16. So now if you add the first 3, that's going to be 5 by 16. So this is approximately 2.18 and so on. Okay, so 7 times 6 by 16, 7 times, so you can just use this because these are cumulative sums. 7 times 8 by 16, 7 times 14 by 16, and as you would expect, the last one is just 7. 16 by 16, which is 7. Right? Because in this, in the formula here also, when you look at the last one, the last k equal to 7, then this is going to be 1. This sum is going to be 1 because this is the sum of all these probabilities. So this sum is 1 and all you will have is L minus 1. So that's 7 here. So these, if you compute, these come out to 2.6, 3.5, 6.12. Okay, and these have to be rounded to the nearest integer values. Correct, because we have these discrete. We are using only discrete elements in the interval 0 to L minus 1. So this one rounded off to 1. This one rounded off to 2, 3, 4, 6, and 7. Okay, so these are going to be the intensity values in the output image. Okay, corresponding to these intensity values of the input image. So wherever you have intensity value 1 in the input image, you will put 0, and so on. Okay, so now this image, or let me just draw it again. So the output image will be as follows. So if you just compare with this, and this lookup table here. So intensity is 0. There is no 0 here. Okay, 1 goes to 0. So wherever there is 1, we put a 0. 2 goes to 1 here. Okay, so wherever there are 2s, we will put 1. Then wherever there are 3s, we put 2, and continue in this way. Okay, so the output image is going to have these values, these pixel values. Okay, so that's the output image. So this is an example of histogram equalization. Okay, are there any questions here? So if there are no questions, I would like to go ahead and start with histogram matching. Okay. So histogram matching is when you don't just equalize the matrix, but equalize the histogram, but you want to make the histogram look like another specified histogram. Okay. Or the specified histogram could be something, a shape that you desire, or it could be the histogram of some other image. Okay. So if you want to match the histogram of the given image with the histogram of some specified image or shape, then you do histogram matching. Okay. So let me just quickly describe the theory. So once the language is all set up from the previous lecture, we can use the same notation and describe this process quickly. So suppose, so all the notation is from the previous lecture. So PRR and PZZ now. Okay, so this is going to be the specified from the specified image. Suppose these are two probability distribution functions. Okay, are probability distribution functions corresponding to two continuous variables R and S. So right now, let's, like before, we will talk about the continuous case and then reduce to the discrete case. So corresponding to two continuous variables R and Z respectively. Okay, so suppose PZZ is what we have, what is specified. Okay, so suppose PZZ is the specified intensity, profile or intensity PDF that we want the output image to have. Okay, then the idea is as follows. So you have an input image. To the input image, you first apply equalization. Okay, sorry. Input image, you equalize. Okay, so input image, the intensities are R. Okay, R is describing intensities of the input image, and this is with the probability distribution function PRR. When you equalize, you will get the equalized input. Suppose the intensities are S and this is your probability distribution function PSS. So on the one hand, you have this with the input image, and on the other hand, you have the specified image. Okay, so either it could be a specified image or it could be just specified histogram. Okay, image or histogram. Okay, so this specified image or the histogram is first equalized. So this also we will equalize. Okay, so this is maybe Z, right? So the intensities here are the variable Z. Okay, and PZZ is given. Okay, so suppose this equalization is done with some function G. Okay, so this function is T, like before, and this equalization is done with some function G. Okay, so that now here you have your S was TR, similarly your equalized specified image or specified histogram is now G of Z. Okay, the intensities are given by G of Z. Okay, so this is the specification, and on the left hand side you have your input. Now what we do is we match this equalized histogram with this equalized histogram. Okay, so we find the matching between these two, and then use this matching to get what should be the corresponding matching between the original intensities. Okay, so we know how to go from GZ to Z. We know how to go from S to R. Okay, so first we match the equalized histograms and then match the original input with the specified inputs. Okay, so that is the process of histogram matching. Okay, and so we'll make that a bit more precise now. So define, so we have to define this G, right, for the specified image. So define G of Z equal to, well, we want to equalize and we know how to equalize, right? So we know that this has to be L minus 1 summation PZ. Let me use a dummy variable V dV. Okay. Oh, this is continuous variable right now. Sorry. So I can just write integral 0 to Z. Okay. So let's define this function G. Okay. And we already know that S is defined as T of R, which is defined in turn as L minus 1 integral 0 to R P R W dW. Okay, so we know S is defined in this way, and now we are defining GZ in this way, and now then the last thing to do is to match. Okay, for matching, we set S equal to G of Z. Okay, so that is to say that G of Z equals T of R. Okay. So you can also express this as saying Z therefore is G inverse of T of R. Okay, so this gives us a connection between these intensities Z and the input intensities R. Okay, but now in general it turns out that computing this function G inverse analytically is not so easy. Okay, so and also we don't really need it because we will not be dealing with continuous functions, we will be dealing with discrete functions. Okay, our values are discrete in reality. So instead of worrying about what is the formula for G inverse, we can just construct a lookup table and then look at the intensities and go back and forth. Okay, so that is what is done in practice. So I'll describe that and we'll do an example also. Okay, so let me just write this remark. Finding G inverse analytically is fairly difficult. And in fact, not required. Since we are dealing with discrete values of R and S. Since we have discrete variables R and S. Okay, we will construct lookup tables instead. But there are only finitely many discrete values to be considered. Okay. All right, so now let's look at, so this was the continuous formulation. So let's look at the discrete formulation. So we have discrete intensity values R0 up to RL minus 1. Okay. And we know that Sk is T of Rk, which is L minus 1. Instead of integral, we have summation PR Rj, j equal to 0 to k. Okay. And this formula holds good for all k from 0 to L minus 1. So this we know for Sk, and now we can take q from this and define our gzq. So remember gz, since it's the equalization, it was given by this formula, right? So in the discrete form, this is summation, L minus 1 summation. Now the function here was pz zj, j equal to 0 to q. Okay, where q varies from 0 to L minus 1. So this is gzq, and we want sk to be gzq. So define sk equal to gzq. So we are, what is this step doing? This step is doing this this matching. Okay, we are going to define each sk to be a corresponding gzq. Okay, where, how is this correspondence happening? Where pz zj is the this is obvious. So, well, so sk is gzq, and therefore zq is g inverse of sk. And to get this, we will simply look at the tabulated values. Okay. So the steps in this computation are as follows. One, you compute the histogram of the input image. So it will take me time to write these steps. What I'll do is I'll just say this and then write down in the notes later. So first step is to compute histogram of input image. Then you equalize to get values of sk. Correct. So this is what I described here. Then you compute values of gzq for the specified image or specified histogram and store these values in a lookup table. Okay. Now for every sk, use those stored values of g to find the corresponding values of zq. Okay, so you do this matching here. Okay, and then that will tell you for which value of s you have a corresponding zq. Okay, you want sk to be equal to zq. So for which z is that happening? You look it up. Okay, and match the corresponding r with that z. Okay, so I think it will be easiest if we do an example here. Okay. So let's do that. So suppose we have So for this, I think I will pick up an example from the text only. So this is on page 145. Right. So this is the example that we are looking at. Okay. So this here is the histogram of a given image. Okay. And this is the specified histogram. So what you want to do is you want to first equalize this and then equalize the given histogram, then match those histograms and then say what RK should correspond to what ZQ. So that's essentially what we want to say, right? What we want to say that which intensity level here should correspond to which intensity level here. Okay. So to give the correspondence between these two histograms, we will go via their equalizations. Okay. So the table. So this is the specified histogram. Okay, so ZQ, whatever we saw here, okay, that specified histogram is given like this. So the values of ZQ, of course, will be from 0 to 7. Okay. And then PZZQ, this is the specified histogram, which means this tells us the number of pixels or the probability that a pixel will have the intensity value ZQ. Okay. So this is the PZZQ. Okay. So now we can just take these numbers. So yeah, here. So this is the correspondence, but no, what I want to get at is the equalized values. So these are the equalized. Once this ZQ is equalized, these are the values of the equalized histogram. Okay, so one knows how to go from ZQ to GZQ, right? We already did that in one example just now. So from going from ZQ to GZQ, you have to go through that entire process and do the mapping. Okay, so this is done. So suppose this equalization is done. Okay, so GZQ is the equalized histogram for the specified image. Okay, and now we have to find the mapping. Okay, so mapping will be so this these same values I'm just going to write here. Okay, so this is the example on page 145. Okay, so let me just write the values. The values of SK, that is the equalized histogram for the input image, okay, are these. 1, 3, 5, 6, 6, 7, 7, 7. Okay, so these turn out to be the SK values for the input image. Okay, and for the other image, the specified image ZQ, the original given values are 0, 1, 2. So this is after round, I think after rounding, 4, 5, 6, 7. Okay, and the equalization of ZQ is GZQ. And these values are come out to be these 0, 0, 0, 1, 2, 5, 6, 7. Okay, so again, these are for some hypothetical image only. Okay, so that is why there are finitely many and only 8 intensity values. Okay, so the now the thing to do is match SK and GZQ. Okay, so when you are matching SK and GZQ, what you want to see is you want to look at the value of ZQ so that GZQ is closest to SK. Okay, so what is ZQ which is closest to? So for example, so when we are matching this, see the matching on this side is going to be, well, one matches with this one. Okay, and then when you have when you don't have an exact matching, okay, then you choose the smaller value. So for example, we don't have an exact matching between 3, there is no 3 here, okay, but you choose a value which is closest to 3, okay, and smaller, so that will give us this matching. Okay, so I will detail these steps when I write it out. Okay, then there is a matching here. Okay, of course 6 matches with 6, okay, and 7 matches with 7. Okay, so now the correspondence between SK and ZQ, okay, will be, well, 1, the intensity value 1 here corresponds to 3. Okay, because this matching gives us this correspondence. Okay, 2 was corresponding to 4, 5 was corresponding to 5, 6 to 6, 7 to 7. So that is, you just compose these correspondences. 3 corresponds to 3, 5 corresponds to 5, 6 corresponds to 6, and 7 corresponds to 7. Okay, so this is what we mean by a lookup table. Okay, so this thing here is a lookup table. We wanted to actually compute G inverse of TR. Okay, but instead of that, we can, because there are finitely many values, you can just do this matching like this. Okay, and hence get the correspondence. Okay, so this is the correspondence. Yes.
Yeah, so ma'am, how does 3 corresponds to 3?
So like, 4 here, right? Sorry, 4. 4, not 3. So 3 corresponds to 2 here, and that corresponds to 4. Okay, so that is that correspondence. Thank you. This is an example of histogram matching. Okay, and if you want to see the results of histogram matching, so there is an example here. Okay. So this is the original image, and its histogram is like this. Okay, so this histogram shows us that most pixels are crowded in the lower intensity levels. Okay, and there are very few and some pixels in the lighter intensity levels. Okay, so clearly we can see that this is a very dark image. Okay, now if you histogram equalization is done for this image, okay, the result is this image. Okay, so the just simply histogram equalization will result in an intensity profile like this. Okay, and the image will look like this. So it looks sort of washed out. Okay, just whitened out. Okay, so this is what histogram equalization does, and it's not a very pleasing effect. On the other hand, what can be done is, so you look at the original histogram, you look at the shape of this. Okay, it is something like this, right? So if you can just keep this shape, but move the intensities to lighter pixels a little bit, okay, then you can probably obtain a better effect. Okay, so instead of getting a histogram like this, this is actually the equalized histogram. Okay, what one can do is you specify a shape like this. Okay, so you have in the equalized histogram, all intensities are lying in this much part. Okay, it will be better if these are spread out a bit. Okay, so the thing to do is to keep the same shape, but spread it out over the entire range of intensities. So that is what is being done here. Okay, so you have that same shape, but the intensities. So we specify this profile. Okay, you can see that the shape is almost the same as before, but only that the intensity levels are spread out. Okay, so we specify this histogram, okay, or this shape, and do histogram matching. Okay, so we will not go into this too much. We didn't plot this out. Okay, but these are the intensity profiles. But anyway, so this is the equalized histogram. Okay, so you can see the difference between not equalized, sorry, matched histogram. So this is the new matched histogram, which we tried to match to this shape. Okay, and this was the earlier equalized histogram. So in the equalized histogram, everything is concentrated here. Okay, very light pixels, and so this is the image. But here now, since the intensities are more spread out, okay, we tried to do this by specifying this shape. The effect looks like this. Okay. So this is the image. This is the effect of histogram matching when we say that, okay, we want the intensities to look in a certain way, and then design or map the pixels to those intensity levels. Okay, so and this is definitely a more pleasing and more clear. The contrast is more clear between the various grayscales, and definitely a better effect than what you have here by histogram equalization. Okay, I think one point, I don't know if I have said this in the earlier lecture or have not said it, but if I have not said it earlier, then I think maybe we can look at an example of histogram equalization. Okay, yeah, so this is an example of histogram equalization. The left hand images are the original ones, and the center column are the equalized images. So what I want to point out is that in theory, we are saying that, the equalized image should have a probability distribution that is uniform, right? So in theory, you have a uniform probability distribution function. Okay. But if you see in practice, this is not actually uniform, right? This is not like a flat. These are not all at the same level. Correct. So this will be the case in practice. Okay. Even here, when this is equalized, you don't see these all at the same level. Although these are equalized histograms. Okay. They are not at the same level because first of all, you have a fixed number of pixels. Okay. And those fixed number of pixels have to be spread out over these intensities. Okay. So it's, if you want to equalize everything, then you don't have those many pixels to fill out that. Okay. Wherever you want to put it. Okay. So in practice, you will not actually get an exactly uniform distribution function. Okay. But the intensities will be spread out over the entire range. Okay. And visually, even though these four, in the last column, if you look at these four histograms, they look different. Okay. So this histogram is definitely very different from this one. But if you look at the image, okay, you don't see, I mean, you wouldn't be able to look at the images and tell that the histograms will look different. Okay. And that is because our perception of images is mostly about contrast. So if the image content is the same in both images, then the fact that the intensities are spread around is more than enough. Okay, so you will not be able to perceive any difference between these two images simply because the intensities are spread over the entire range. Okay, or spread over the same range in both the images. Okay, so it makes no perceptible difference, even though these two equalized histograms look different from each other. Yeah, so those were 2 points that I wanted to make. One is that these will not look like a uniform distribution function for practical reasons. And secondly, just because the histograms look slightly different, that difference will not be necessarily perceived in the original images, okay, or the transformed images. Okay. So are there any questions so far? So in your homework, you will have, I think, exercises for both histogram equalization, histogram matching. Okay, so this is the same process that you will do with. So histogram matching, I'm actually expecting you to, sorry, histogram equalization, I'm actually expecting you to write the full code, okay, and compare it with OpenCV's function. Okay, so that shouldn't be too hard. But let me know if you require any help. So what I will do next time is talk a little bit about local histogram processing. But in the next lecture, we will be done with histograms or histogram processing and start talking about spatial filtering, okay, convolutions and stuff like that. So I can stop the lecture now if you don't have any questions. All right, so let's stop. And we'll meet again on Tuesday.
Good.
Yeah.